So we're going to look at central limit theorem, which applies to all types of distributions, discrete or continuous. What type of distribution have I got there? Discrete. Okay, you can clearly see I've got a discrete distribution. Would you describe that distribution as normal? Why would you not describe it as normal? What should a normal distribution look like? Yep, nice bell curve sort of shape. Would you describe that distribution as anything? I would not. You could have a linear or a constant distribution where it's a straight line across the top. That's not the case. So this is a pretty irregular shaped distribution, isn't it? Happy with that? I'm going to give you this 1, 2, 3, 4, 5, 6. That's their dice scores. And this is Beddington's dodgy gambling facility, where he's loaded these dice so that you can't get a 3 and a 4. If you get a 3 or 4, you win. Ignore that as an example, but that's just the context for what's going on. If you were to roll these dice a million times, you'd find the probability of getting a 1 is what? 2? 3? Oh, sorry, 5 and 6 is 0.25 as well. You can't get a 3 or a 4. So that's what I've set up with our distribution. Happy with that? I'm not going to say much about central limit theorem at this point in time. What I'm going to get you to do is to calculate your means. So what I've done is I've selected a sample. So I've just said I'm just going to roll the dice 4 times and see what I get. Can we calculate, before we go any further actually, the mean of this distribution? What would you expect? What's the expected value of that distribution? Remember that goes sum of that value there. So it'd be 0.25 times 1. And that gives us 1.5, 3, 3.5. So our population's mean, so the population has a mean of 3.5. Cool? So in your head, what I want you to do, so before we go any further, we'll get these means down, and then we'll start talking about that. So, Lily, what did you get?
I didn't do it.
Okay.
Yeah.
613 divided by 4. 3.25. What did you get? Who's 2? Jackson, what did you get? Yeah, done your mean? 3.25. Six. 5 point. Sure about that? I think you might have. What's 7 plus 7? 14 divided by 4. What's 14 over 4? 3.5. Maybe it's you know what I think it's done is you've not put brackets around. It's done the 5 over 4. Added that to the rest. I don't know, could be. 2.5?
3.75.
3.
What do you notice about those numbers? They're all around 2, 3. I've made these numbers up. But do they look like plausible values? Is that what you'd sort of expect for that distribution? So what I want you to do now is just to quickly draw this in your book potentially, and I want you to So same values, 1, 2, 3, 4, 5, 6. I want you to place dots above each other where you think that's occurring. So to give you an example about what I think that should look like, I might even just move that. To give you an example, my first value is at 3.25, so I just put a dot there. My next value is at 4.75, so I'm going to put a dot there.
What's the word on the side?
Occurrence. So this is the number of times it occurs. So as you're doing that, I want you to think about what that looks like compared to the original function. Are they similar or are they not? I'm going to ask you about that once we get through that. So. Give you 10 seconds to finish putting those dots on. So Ethan, what do you notice about the dots comparing it to our original distribution? It's the opposite? What do you mean by the opposite?
Like, the dots are more in between 3.4 where there's nothing.
Yep, so there's nothing in the 3 and 4 section. If we had some columns in the 3 and 4 section, do you think that would change it or not?
Yeah.
So if it was a fair dice, so think about what's this? What's this represent?
Oh, well, if that had numbers in it, would you have changed those?
But how would they change it? What's that represent?
The mean.
Mean? So if this was a fair dice, would the mean change? Would it be what would the mean? What's our mean sitting around?
Oh, it wouldn't change if you weren't using 3 and 4, but using numbers there.
So what do you notice about if I was to do this a million times, what would you expect it to look like? All in the middle? Every data in the middle? There'd be nothing outside? There'd be a few, but most of them would be around the middle. Interesting. What's another distribution? What's something that has lots in the middle and a couple on the outside, a few on the outside? A normal, what? Bell curve, normal distribution. Okay, is that normal? But when we take a heap of the sample means and we repeat it over and over and over again, we get a normal distribution. What would happen? So how many values have I taken to get my mean? What do you think would be the impact of changing that to say 100 values? So if instead of taking 4 dice rolls, if I took 100 dice rolls, what do you think would happen? Have a think. What does this look like? Because where should this bell curve be centered? Between 3 and 4. Why do you say 3.5? That's the middle of this. That's where you expect. That's where you expect your mean to be, don't you? So you'd expect most values to be in there. Okay. Is it on 3.5 or not quite exactly, or we can't quite tell that? It's pretty close, but it's not exactly there. If you did 100 trials, what would you expect? If you flip 2 coins, are you guaranteed to get a head and a tail? If you flip 100 coins, so if you flip 2 coins, are you more likely to get 50-50? Or if you flip 100 coins, you're more likely to get around 50-50? Is it?
Yeah, because your odds aren't changing.
What's the chance of you getting no heads if you flip 2 coins?
7.5. Oh, no. Oh, yeah.
So the more numbers we add to this mean, what's going to happen is you're going to get closer to our 3.5 value or further away.
Right, like, are you adding more?
So if I did more trials to get my mean, what would I expect? Would I expect to see a 4.75? Would that happen?
No, you get further away.
Would it?
No, wait, are you just adding 1, 2, 5, and 6 to it?
What if I did 2 trials? Let's take that out. What if I did 2 trials? So instead of doing 4, I do 2.
If you're closer.
So if I took out...
That was a bit further away.
You only have 2
Like if you have 1 and 6, it is.
So what's the mean of... If I just took the first two, let's use this data set. What's the mean of these two? 3.5. What about these two? 3. What about these two?
5.5.
5.5. What about these two? Are those values closer or further away? They're going to be more dots out here, aren't there? So if I then add more numbers, so if I do the opposite of that, what do you expect is going to happen? So I'm going to get a curve that looks like that, aren't I? Around 3.5. If I did 100 trials. Cool. So what's that telling you about the number of samples that I take to create my mean? Does it matter?
Yeah.
It affects it? How does it affect it?
Because you can see it like Theorem.
More accurate.
Why is it more accurate?
Because it's a bigger spread, or it's a bigger...
More samples. Bigger samples.
Bigger sample size? How does a bigger sample size help? You're right. How does a bigger sample size help? Would you say it more accurately represents the population? Like if you do a sample of 1 student, is that a fair representation? So if I was to go and ask 5 kids whether they thought lunchtime should be shorter, and 4 of them said yes, would you say that represents the population? But I could probably randomly fall upon 4 kids that say that. Or, I don't know, if I asked 10 students whether they should reduce the phone usage of St. Pat's, and 9 said yes. So the central limit theorem is all about the fact, is that distribution normal? What happens as I take samples and I take the mean of their values? What does it turn this distribution into? A normal. And where does the mean of that distribution lie?
At the mean.
So the mean of this is? And the mean of this is? So what happens is we turn our irregular distribution into a normal distribution with a mean at the same point. What occurs with standard deviation? What's standard deviation talking about? It's about the spread. So what point am I trying to make with standard deviation? What impacts the standard deviation of my normal curve? What about the data?
The spread of the data. The sample.
Did the spread of this data change? But how did I make that get really tall and thin? More what? More trials. So I added more samples to my population, to my sample size, didn't I? I increased my sample size, and that made the standard deviation go
Closer down, towards it.
down. Down. Cool? I'm going to give you an equation in a second to help hopefully make meaning of that. But I'm asking a couple of questions before I do that. Would it matter what this distribution looked like?
Yes.
No, it's
It's more likely to get a 6.
I know, because the mean would be the
Your
same.
mean
Right?
would-
My mean would move, but would it still be normal? Or would it be a normal distribution? Would it be that bell curve?
Yeah, still would be. Just might be a different.
Like, would that graph still be?
If I say I doubled the chance of getting a 5 and a 6 and halved the chance of getting a 1 and a 2, would that produce, the mean would shift, we've agreed with that, the mean would move, yes, but would it still be normal?
That's fine.
Yes. So the central limit theorem is all about that, and that's the crux of the normal distribution, that providing you take an adequate number of samples, if you graph the means, it will form a normal distribution. And the standard deviation is affected by what? The number of trials that we use to create our mean. And that's the crux of the central limit theorem. Cool? Alright, I'll do that formula.